Greetings everyone, this is Cal Poly IME Engineering Team 8. Our project is Resource Allocation and Optimization for Brainstorm Studios. Our advisors are Dr. Acquisian and Dr. Placencia respectively. Team members are Wendy Lamb, Manufacturing Engineer, Sean Bile, Industrial Engineer, Rizwan Nakvi, Industrial Engineer, Gabina Arguello, Manufacturing Engineer. Brainstorm is an ed-tech startup located in Irvine, California. They develop products and curriculum in the STEM education space and offer specialized classes from elementary to high school. Our project will consist of designing and the implementation of a SQL database, optimizing a warehouse facility layout, forecasting future sales of a robot activity mat, determine if manufacturing 3D printed game pieces in-house can meet demand of future sales, and lastly, redesigning a robotic chassis. Next, Rizwan will talk about the first aspect of our project, designing and implementing a SQL database.
The problem with the current inventory system is that it is too static, outdated, and has very little accountability. Audits take too much time, and management has a low visibility of the equipment. Our objective is to develop a SQL database for equipment, test for failures within the system, and take preventative action, and finally implement the database into the warehouse system. The previous system was a printed Excel spreadsheet that was unable to update regularly and had a risk of missing information. Missing equipment could not be found or traced accurately to the instructor that had originally checked it out. The database was a large part of the future warehouse system, so a V-model approach was taken for project planning. The early stages of the project involved defining requirements, interviewing stakeholders, identifying failure modes, and building a detailed design architecture for the system. It also drafted requirements and procedures for maintenance of the system. After that, the building and testing phases were worked on and used the early requirements and possible failures to avoid bugs related to the already identified issues. Finally, the integration, operation, and maintenance portion of the project lifecycle ended the team's involvement with the company. Since the completion of the project is still very recent and COVID has limited the amount of time spent on site, data and performance measures are not easily accessible to the team. Early in the system design process, the team held multiple interviews with system stakeholders to identify requirements for the system. Interview questions were prepared so that a broad answer could be given first, then narrowed down to feasible requirements with clear baselines. Failure mode and effect analysis was also done by working with the stakeholders in a team meeting to identify any issues before system creation. FMEA was done both on the process of kit storage and retrieval and on how the database should be designed and created. The information in the database is stored on a SQL database. The graphical user interface was created using PHP and JavaScript. The server is hosted on GoDaddy.com. Kits were given a barcode on their bins that could be read with a handheld scanner. It allowed for real-time inventory audits, reduced the time for kit check-in and check-out, and was able to update managers to required maintenance of kits based upon the number of uses. It also alerted managers if a kit was past due and not returned to the warehouse. The warehouse originally had the accessories near the 3D print wash station. Since there are two different accessory locations that are spaced so far apart, there was a lot of travel time between the two. In the updated system, the accessories were moved to be closer together, and the print station was moved closer to the wash station. A new class cart queuing area was also installed in preparation for the future system. The kit pulling system originally required instructors to pull their own equipment, but in the future system, there are dedicated employees who retrieve kits from the shelves and place them in a new queue for instructors to pick up. Using the recommendations for the future state and incorporating the database, layout improvement, and queuing system into the warehouse, the kit check-in and check-out cycle time was reduced by nearly 65%, from 12 minutes and 48 seconds to 4 minutes and 33 seconds. The estimated cost savings utilizing the future system is approximately $12,000 per year, and 825 labor hours are saved per year. This was calculated based upon 25 class carts per day at $15 an hour wages. Next, Wendy will talk about the robotic activity mat sales and game pieces.
Brainstorm is currently trying to project future sales of their new robot activity mat. Each mat uses 3D printed game pieces. We want to know if they can meet future demand manufacturing in-house. Our objective is to forecast future sales of their new activity mat product, optimize current 3D print manufacturing processes, and determine game piece scalability. The robotic activity mat is a brand new product for Brainstorm. Our team was able to acquire sales from January 2020 to June 2020. With this data, we were able to forecast future sales through October 2020 with upper and lower bound confidence levels. Current state has a unique design and custom look. It's 3D printed, however, it has a low production capability and is labor intensive. One alternative our team looked at was injection mold game pieces. Plastic injection mold offers a unique and custom design that is similar to Brainstorm's current piece while providing high volume production. Unfortunately, due to financial restraints, the mold itself is not feasible at this current time. Here, we tested alternative manufacturing processes, and we concluded outsourced foam game pieces offered high volume and scalability while reducing cost per game piece. Brainstorm's new partnership with Amazon and Gaia required Brainstorm's ability to scale up the game pieces immediately. This resulted in having to outsource game pieces with a third-party manufacturer that produced foam game pieces. Above is an example of one they produced. With our recommendations, Brainstorm will have an estimated cost savings of about $97,000 while reducing 5,200 labor hours based on the average of 1,200 activity mats sold per year. Next, Gabino is going to talk about the redesign of a robotic chassis.
Brainstorm Vex robotic platform is currently experiencing stress fractures and cracking, causing the robotic chassis to fail. In order to remedy this, our objective was to analyze the current manufacturing process to find the major defects in the chassis. Once those defects were found, alternative materials were tested in search of a stronger, more durable chassis. Once the new material was selected, we plan to implement this material into the redesign and standardize the new chassis. The current chassis is printed using the FDM printing process. It is printed using the material PLA plastic utilizing a honeycomb pattern. The company is only using a 30% infill density in order to reduce material costs and keep print time around 5 hours and 40 minutes. The vertical wall shown by the red arrow experiences stress fractures and cracks resulting in a 16% failure rate. Alternative production methods were considered, including aluminum casting, sheet metal, and plastic injection molding. The chassis will require a heavy modification for it to be castable, and even then, the casted model would be too dangerous for some of the smaller children to handle. A sheet metal version will require intricate design to completely remove burrs and make safe for children. Due to the current demand of the chassis, plastic injection would be too costly. The current demand does not justify using plastic injection as a production method. Figure 1 shows the original CAD design, while Figure 2 shows the castable part. A rendering of the cope and drag were constructed using Fusion 360. In order to add strength to the chassis, trusses were added to the redesign. This triangular shape greatly improves the strength of the chassis, resulting in a lower failure rate. In addition to redesigning, the material was changed from PLA to ABS plastic. ABS plastic has superior durability characteristics over PLA. Although ABS is harder to work with over PLA, the improved ductility is better suited for end use. The infill density was increased from 30% to 55%, resulting in an estimated failure rate of 1.3%. Highlighted by the animation, you see once again the truss that is utilized to reduce stress fractures within the chassis. With the failure rate reduced to 1.3%, we saved 28 labor hours and an estimated cost savings per year of $420. We were able to accomplish this by reducing the number of replacement chassis that need to be reprinted. This time saved opens up the 3D printers to be utilized for purposes other than replacing broken parts. And now here is Sean with our closing remarks.
Project conclusions. The SQL database now provides real-time metrics, allows system updates and future iterations. It also saved about $12,000 per year. For the robotic chassis, we reduced failures, created an efficient, safe, and scalable design, and also saved about $420 per year. Game pieces are now outsourced, allowing for better uniformity and exponentially higher production. This saved Brainstorm about $97,000 per year, as opposed if they were to continue manufacturing in-house. Warehouse operations are now standardized, have better process flow, and have an optimized pooling and queuing system for class equipment kits. Our economic analysis shows current costs for warehouse operations, game piece production, and robot chassis manufacturing. Their current system estimated cost is about $125,000 per year. With our future state recommendations, they'll save around $110,000 a year. We expect our system recommendations to be viable for at least 10 years. Some of our recommendations to Brainstorm were to outsource robot activity mat game pieces, move stored accessory kits together, optimizing process flow and eliminating wasted movement in the warehouse. Lastly, to incorporate the cart queuing system for instructors' class equipment. Our engineering team would like to thank the whole IME department for their help with our project, but most importantly, Dr. Equizin and Dr. Placencia as our personal advisors. We appreciate your time, energy, and commitment to all of us IME students. We would now like to open up this time for discussion.